Hi, this is John Whitney. In this video, we will continue the discussion of design from a chemical engineer's view. Here is the second example from my career. Design and development, getting the materials, the equipment, and the process conditions to dance together, laser welding inside an inkjet printhead. The product, a new type of inkjet printhead, was proposed, there to be cheaper, but a much bigger engineering challenge. The problem. The responsibility I was given was to develop a reliable method of sealing an ink tank lid to its body. Unfortunately, in this case, reliable meant several things. I would have a much tighter pass-fail leak specification. Holes larger than about 10 to 20 nanometers in diameter would be a failure. Sometimes I would describe the specification in terms of how many carbon atom diameters it was for those that had a hard time wrapping their heads around nanometers. I did not have a method to test leaks many times smaller than the previous specifications, so a whole new leak test method would need to be developed to prove that our assembled parts met the new specification, and the leak test method would have to be qualified to prove that the test method itself was valid. The frequency of leaking parts that made it to the customer would need to be very close to zero, because with this design, a failure would cause the whole printer to fail and not just the printhead. Although glues could be used during development, in production their material cost would be too great and their time to cure in the manufacturing process would cost too much. The solution. I did a survey of all the possible methods of welding plastic parts. I talked to all the major plastic welding equipment suppliers, especially their development groups, and reviewed the few textbooks on the subject. For my own use and to be able to present it to others, I put the information into an Excel spreadsheet. Once I came to a conclusion as to which type or types of welding should be tried, I would need to have solid justification before we bought equipment for initial bench scale testing. At the same time, I started contacting leak test equipment manufacturers. In this case, there was one really good reference book on leak testing. It described what test methods were available, how they worked, what range of leaks they were practical for, and what types of errors they were prone to. Their information went into a similar Excel spreadsheet. The surveys narrowed the field down to a few choices. The possible welding processes were some laser welding processes that were new enough that they were mainly used in university labs, but if they worked, could have great reliability, versus a hot plate method that was proven technology, but would always be a mess and a headache for manufacturing. We would try the laser welding and try not to end up with a headache for manufacturing. There was only one possible leak test method. It had been tried a few years before in production and failed spectacularly. Its failure was so spectacular that it was the stuff of legend, and it was my only option. Darn. The first laser welding equipment I bought had never been fully built or tested by the manufacturer before, and it was still the best available. I worked with their equipment development group, helping them debug their equipment and make it more robust. Laser welding molded parts was so new that there were no design guidelines for how the plastic part should be shaped just before welding, so I would need to develop a reliable weld joint and specifications for those molded parts also. In this case, laser welding parts involved a very powerful and intense laser projecting its light through the lid and onto the top of the body. This project just happened to come along when powerful lasers were coming down in price enough to be used in manufacturing and not just development labs. For the system to work well, intense heating was needed in specific places and almost no heating everywhere else. The laser light would go through the lid, so the lid needed to be very transparent to the wavelength of the light the laser produced. The body needed to be very opaque to absorb a very high proportion of the light within the first 1/10 of a millimeter of body plastic. If done right, the body joint would warm, soften, conform to the lid, conduct to the lid, and then the lid would warm enough to cohere to the body. Insufficient heating would leave the body conforming and adhering to the cold lid like a solder joint, instead of having both the body and lid conform and cohere to each other like a welded joint. Welded joints are much more reliably leak-free and stronger during impact. For this to work well, the softening temperature ranges of the lid and body needed to be very close to the same, so the same base polymer was used for both. Carbon black was used in the body to create very high opacity, and a newly developed dye was used to color the lid that had very low opacity to the laser wavelength, but looked opaque to the human eye. Also, in order to make it more reliable, I wanted a wide heat sealing temperature range, so a broad molecular weight distribution was desired in the base plastic. After a number of equipment and process changes on the laser welding and joint design, welded joints were produced that reliably met the specification. For a short time, we were the largest manufacturer of laser welded molded plastic parts in the world. I got several patents out of the work. While the laser welding development was going on, the leak testing development had to keep up. I made some quick in-house leak test equipment that pushed the limits of pressure decay leak testing to get something going quickly. My only long-term leak test option was helium leak testing. This is testing that can measure helium atoms going through a solid steel plate and will get confused by the few helium gas atoms left on a part from a previous test. It uses a mass spectrometer to measure the concentration of helium atoms. There are lots of ways to goof up with this style test, and the equipment is not cheap, so I spent time with a good quality leak test equipment manufacturer to get a jump start on my leak testing education. I bought a small helium leak tester and designed my own equipment to hold the parts to be tested, and started to develop a test sequence for my parts. The test method used in development and later in production could detect a leak 1/10 of the leak specification. You desire a test to be able to measure to 1/10 of the specification so that you can clearly know if a part is good or bad, and don't have many parts that are so close to the specification that you're really not sure if they are good versus bad. Although production management did not want a helium leak test, I was able to convince them that it was the only option with the specification we had. After many conversations, demonstrations, and trials, they accepted the helium leak test equipment. One measure of success was that on a later product that I was not involved with, they chose to use the helium leak test equipment over other options. Conclusion. I found more common to the design development role in chemical engineering was the development on full-scale equipment. Working with bigger, more expensive things requires you to be very thoughtful of your testing and modeling. I also found more common in chemical engineering was the co-development of the material and the process to make it. For me, working on a technical challenge with knowledgeable, friendly people is a lot of fun. The more technical, the better.